Hey guys, welcome. If you haven't watched my introduction video on complex integrals, then you should, because not just what's said in this video, but what will come in later videos will depend in part or in whole on your understanding of what's discussed in that introduction video, which I'll link below this video. Yeah? All right, now the topic at hand is the evaluation theorem and its proof for complex integrals. And the evaluation theorem for complex integrals is akin to the evaluation theorem for calculus of real variables, which is sometimes called the fundamental theorem of calculus part 2. As far as I'm concerned, there is no fundamental theorem of calculus part 1 and part 2. There's just the fundamental theorem of calculus, which is the one that says that the integral of the derivative is the function itself. But anyway, that's just a side note. Let's get started here. So suppose that capital F of z is an analytic function, meaning that it's differentiable. We say analytic instead of differentiable when we're talking about functions of a complex variable. Anyway, given that capital F of z is analytic, and we have that little f of z is the derivative of capital F of z, and little f of z is continuous in a domain D, then for a contour C lying in the domain D with endpoints z1 and z2, this is true. And so this is the statement of the evaluation theorem. And now here goes the proof. So the proof goes like this. First, the integral over the contour of little f of z dz is equal to this here. And you should know that if you've watched the introduction videos I told you to do so, right? I explained there why this here is the same as this here. And of course, this here is the same as this here, because we claimed here that little f of z is equal to the derivative of capital F of z. Yeah? Okay. But then, this in turn means that we could rewrite this in this fashion if we so chose, right? And that's just saying that, like, the derivative of capital F of z of t is little f of z of t times z prime of t, right? That's all we're saying here. All right. But then that means that, undoing this integral sign in the derivative and evaluating, we see that we have that this here is the same thing as f of z of b minus f of z of a. But wait, z of b is z2 and z of a is z1, so we can write this more succinctly as f of z2 minus f of z1. Yeah? Okay, so this is the proof, and an important corollary to this, and this corollary, which we'll come upon again in later videos, is a very, very important corollary. You need to know this, as it simplifies a lot of complex integration. And what it says is that, like, if z1 and z2 are the same points, that is that we have like a closed contour, then the closed integral over that contour of little f of z dz, which is the same as this, is 0. This is a very, very important result. Yeah? Okay. And we'll see this in practice, this corollary, and examples to come. Yeah? All right. I hope you enjoyed this video, but this is it for this video. All right. Keep watching. Take care.